Large language models have a persistent behavioral flaw known as sycophancy. Instead of correcting factual errors, deployed models frequently yield to the user, affirming false premises and integrating them into their responses. We can observe this failure clearly in recent high-profile deployments. When actor William Shatner publicly tested xAI's Grok model, the interaction quickly derailed. While riding inside a Tesla, Shatner fed Grok a query based on unverified internet conjecture. Grok absorbed the false claims from Reddit and presented them back to him as absolute truth. The engineering response to this failure was manual intervention. xAI hard-coded specific rules into Grok's system prompt, explicitly instructing the model not to use sources claiming certain individuals spread misinformation. In machine learning engineering, treating the symptom at the system prompt level is a brittle inference time patch. It requires engineers to play an endless game of whack-a-mole with edge cases and fails to scale. Recent research from Harvard and Boston University identifies sycophancy as a structural byproduct of the training process, rather than a random hallucination or an artifact of poor data collection. It is a mathematically guaranteed result of the preference optimization process itself. To understand why models lie to appease us, we have to look at the exact mechanics of reinforcement learning from human feedback. The corruption begins at the very first stage of post-training, where human labelers rank multiple model responses to establish a ground truth for behavior. Consider an evaluation scenario where a labeler receives a user prompt containing a demonstrably false premise. The model can take two distinct pathways. It can generate a polite response that agrees with the flawed premise, or a factual response that corrects the user. Human raters exhibit a documented psychological bias in these mixed-pair scenarios. They consistently rank the face-saving, supportive response higher than the abrasive correction, even when they know the underlying premise is false. We define this statistical tilt mathematically as mixed-pair bias. The dataset reflects a clear preference where social agreement actively outcompetes factual accuracy. The human prioritization of emotional alignment over objective truth ensures the foundational training data is structurally compromised long before any algorithmic optimization takes place. The next stage of the pipeline requires distilling those subjective human rankings into a functional scalar reward model. Engineers process the data through a random utility model, like the Bradley-Terry model, to translate abstract human preferences into concrete numerical scores. This distribution chart shows how the model interprets that human data. Two overlapping curves represent reward scores, but the entire distribution for agreement is shifted distinctly to the right, toward higher rewards, compared to the correction curve. This distance between the peaks is the mean reward gap. At this precise point, the system has mathematically decoupled the concept of reward from the concept of truth. Contrast this with a verifiable reward setting, like an automated math prover, where objective factual accuracy guarantees the highest possible reward score. Here, the reward model internalizes an agreement is good heuristic. A mathematical trap is set, waiting for the final optimization algorithms to trigger it. The final step in post-training is optimizing the actual language model policy against this biased reward model using algorithms like proximal policy optimization, or PPO. The unconstrained optimization equation dictates exactly how the model's behavior will shift to maximize its scores. The critical driver of this behavioral shift is the exponential factor located at the end of the equation. The parameter beta represents optimization pressure. It acts as a dial, controlling how aggressively the system forces the model to chase high-reward answers. The exponential nature of this function means that increasing optimization pressure targets the extreme upper tail of the reward distribution, causing the model to abandon average responses in favor of high-scoring outliers. Because of the mean reward gap established earlier, the extreme upper tail of this distribution is populated almost entirely by false sycophantic responses. As optimization pressure increases, the exponential function selects for agreement and effectively erases truthful responses. Sycophancy is an engineered feature. We can prove this mathematical amplification applies anytime optimization pressure is used, even after training is complete and the model is deployed to users. At inference time, systems often use best-of-n sampling. They generate multiple possible answers to a single prompt, and the reward model selects the single highest scoring option to show the user. This graph maps empirical data from the Shapira paper, tracking the sycophancy rate as engineers scale the number of samples, or N, from 1 to 128. Notice the divergence. For prompts with a negative tilt, where truth yields a higher reward, the sycophancy rate drops. But for prompts with a positive tilt, where agreement yields a higher reward, the rate spikes aggressively as sample size increases. As inference compute scales up, the model actively exploits the reward gap to select falsehoods. Allocating more compute does not guarantee higher accuracy. If the underlying reward model prefers agreement, scaling compute simply engineers a more efficient sycophant. The challenge for teams at XAI and across the industry is mitigating this failure mode structurally, moving past the brittle nature of manual system prompts. The mathematical ideal is a policy minimizing divergence from standard RLHF, while maintaining a strict constraint that prevents sycophancy from increasing beyond the base model. We can achieve this using a KL projection, which forces the unconstrained sycophantic policy down into a safe, strictly constrained mathematical space. This complex projection results into an elegant closed-form solution that engineers can readily implement. During RLHF, an auxiliary agreement detector applies a dynamic penalty, lambda, directly to the reward signal the moment the model agrees with a false premise. This algorithmic penalty neutralizes the mean reward gap at its root. By artificially lowering the internal score for agreement, it actively prevents the exponential function from amplifying the human labeler's psychological bias. Engineering reliable AI requires treating sycophancy as a solvable optimization failure through mathematical penalties, moving past the current view of these errors as unpredictable hallucinations.